Okay, so that was the result I'm going to talk about were obtained, in fact, a few years ago with Alexandre Eudes, who was a postdoc at that time, who is now engineer researcher at Onera, and Glauco Scandaroli, who was a PhD student. And so that's not, so as I said, they were obtained a few years ago. But one of these results, which was in the thesis of Glauco Scandaroli, was not published, and so I found that it was a good opportunity to, with this conference, to publish this technical, little technical result. Okay, so we've heard about observers. We will go back maybe 40, 50 years back with linear observers, in fact. So you may find that a little bit strange. So the content of my talk, I will talk a little bit of the context. Then I will provide the technical result, which may be viewed as the main result of the paper. And I will talk also about application. So that's this part on application is not just an application of the result, but it also contains another idea which can be interesting in observers or observability problems. And finally, some remarks and conclusion. So, of course, everybody here knows that there is a rich literature on observer design in both linear systems and nonlinear systems. Essentially, for linear systems, even time varying, we are able to obtain global convergence properties if the system has some kind of observability properties, and we may also obtain optimality properties in some statistic sense. For nonlinear systems, we also know that usually, even if there are lots of approaches to deal with these systems, it's very difficult to get global convergence properties of observers. And so basically, the thing that you will see in this talk is motivated by this difficulty. In some cases, as you will see, a nonlinear system can be, in fact, lifted into a higher dimensional state space, and it can be made linear due to this lifting. And the interest, of course, is that then you can use results from linear systems theory. And we know that these results are very strong, especially in terms of convergence. So basically, as I say in this talk, there are two parts. The first one, which is a technical result on observability of linear time-varying systems. A result of the PhD of my student Glauco Scandaroli. And the other part is the illustration of this idea of lifting to a robotics estimation problem. So I will start with a short recap on observability of linear time-varying systems. So x dot equals a of t of x plus b of tu. The measurement y equals c of tx. So throughout this talk, I will make the assumption that a, b, and c are continuous and bounded function of time on 0 plus infinity. So these are very well-known classical definitions. So the system, this system LTV for linear time varying, is uniformly observable if there exists some constants, tau, delta, strictly positive, such that the following inequality, W of t plus tau, is larger than delta I is the identity matrix, where W is the observability gramian of the system. So this observability gramian is defined through the state transition matrix of the system. So of course, that's standard, and it's also well known that usually this transition matrix can't be computed. So that's a difficulty with this formulation of uniform observability. Another tool which is usually used in linear time varying system is the observability space. which is defined, for example, in the classical book of Chen on linear system theory. So N0 is just the matrix C, and the following matrices N1, N2, etc. are defined recursively through this definition. So of course, in the time invariant case, O, the observability space, is the standard Kalman observability matrix. So it's a finite dimension matrix. In the time varying case, you may have an infinity of elements. And we also know that in the time varying case, the rank, if the rank of this observability matrix is equal to n, this implies some kind of instantaneous observability at time t. So now I will start with the first result of this paper, so this technical result, which basically is a sufficient condition for uniform observability of linear time systems. And so the objective is to be able to prove uniform observability in a, I would say, simple way. So of course, without having to compute the transition matrix. And so this proposition, which is here, says that if there exists a positive integer capital K such that first the time derivatives of A and C are sufficiently regular, which means well, the Castle order derivatives are well defined, unbounded on for all time up to K equals capital K. And if there exists a submatrix M composed of the observability matrix here, so basically a submatrix M and two scalar delta bar and tau bar such that there's a capital E missing here for the identity matrix, such that the integral of determinant of M is larger than delta bar times the identity matrix, then the system is uniformly observable. So basically, the idea is that this will allow us to check uniform observability simply using element of the observability matrix. The nice thing is that this is an integral formulation, and so it's in some sense consistent with the classical definition of uniform observability. A small remark, after we obtained this result, we found that there was a similar result obtained in 2010 by Bristow, Petit, and Prali. So that's basically the same idea of using the observability matrix, but in their paper, they required positivity at each time instant. Basically, that's some conditions which was close to requiring that the determinant of M of t was larger than some threshold for any t. In our case, we only require it in some sense on average. So that's so the proof of this result is in the paper. So that's essentially the main contribution. And now I will come to the application. So the application is to a molecular visual inertial problem. And so we've heard in the talk before on the problem of estimation with visual inertial sensors. So basically here the framework is the following. You imagine that you have a planar target, something that you can observe with visual, with a camera, monocular camera. With the camera, you also have an attached IMU. And so at some initial time, you take a picture of the visual target. So that's the initial time and the reference frame, I would say, R star. And from there, you would be able to estimate all the state and velocities of your systems at any time t. That is, the system, for example, here an helicopter moves, and you would like to estimate rotation, position, etc. So the difficulty, of course, is that you have a monocular camera, so you don't have depth information, and you only have the measurement by the camera and the IMU. So the goal is to estimate, as I said, both the 3D motion, that is the rotation matrix R, and the position P with respect to the initial configuration, the velocity, and also the normal and distance to the plane at the reference image. And so what you get as measurement, you measure essentially what we call the homography matrix. So that's something that can be computed from the visual data, and it is defined essentially by these relations. So it's a combination of rotation information and position information, but it also depends on the unknown, which are the normal to the plane and the distance. And you also have the measurements given by the inertial measurement unit, that is the angular velocity vector and the specific acceleration. So this problem has had already been studied in some papers. So, for example, there was a first solution provided by a paper by Servant, Houlier, and Marchand in 2010. In their case, so they took as a state vector the quantity that we want to estimate, and as measurement the homography and angular velocity, specific acceleration. So what we see, of course, the rotation matrix satisfies these well-known kinematic equations, and the position vector satisfies these equations with G star, the gravity expressed in the reference frame. And so we have here dynamics which is linear, but we have a measurement h which is a nonlinear function of the state. Since, of course, you have this relation here where you see that you have products of R with P, etc. So in these formulations, you still have a nonlinear estimation problem because your measurement is a nonlinear function of the state. A second solution that we developed a little bit later with Robert Mahoney, Tarek Hamel, and Ezio Malis was to change a little bit the definition of the state, to take as state the homography up to a scale factor. In this case, h bar belongs to the special linear group, and so that's interesting because we can make use of properties of Lie group for estimation. And so we also included in the state this matrix M, which gives some information on the velocities, and the normalized, the scaled normal vector to the planar target. And the measurement is given by h bar, omega, and as. So in this case, the measurement h bar is a linear function of x, since x h bar is the first element of the x. But the dynamics, so I didn't write it here, but if we write the dynamics of h bar, it's a nonlinear dynamics. So again, in this case, we have a nonlinear estimation problem, because the dynamics is nonlinear, but the measurement is linear. So a third solution that we proposed is essentially the following. So that's another idea which you may find interesting, is to lift the estimation problem in a higher dimensional space. So basically what we do is that we keep the original definition of the measurement, so the matrix H, omega, and AS, and we define the state as H, the matrix M that we've seen before, the scaled normal vector, and this matrix Q. And if we take this X and we write the dynamics of the states, what we see is that we have something which is linear in the state. So of course it's linear time varying because it has dependence on omega, which may be viewed as a time function, on AS, which is also a time function. But this depends linearly on all the components of the state. And so finally, what we get is a dynamics which is linear time varying, and a measurement which is a linear function of x. So basically, we come back to the linear time varying framework, and we can make use of the lemma that we've seen before, but we can also make use of all existing results for linear filtering or linear observers like Kalman, standard Kalman filtering, or Luenberger observers. And so based on this, we could show that so this sufficient condition on observability, which is essentially that the integral of the derivatives of the specific acceleration plus omega times the specific acceleration is always, so the integral on some interval is always larger than some threshold. Two remarks. First remark, this can be written more simply as just the fact that the integral of the linear jerk is larger than some threshold for any time interval t plus tau. So that's more physical as an interpretation. And however, this condition is still useful because we can use this condition to check in real time loss of observability. We see that basically to have observability we need motion. We can't have observability if we don't have motion. And using this quantity, which is basically measurable because we measure omega in real time and we measure the acceleration in real time, we can check in real time if at some moment we have loss of observability, and we can adapt the observer gains in real time to avoid to try to estimate the state when we are not observable. So that can be useful. Okay, just so to conclude, essentially there are two ideas in this paper. The first one is this sufficient condition for uniform observability of LTV systems. And the second one is the illustration for robotic problem via lifting. So basically transforming a problem which is originally nonlinear into a linear time varying problem. And of course, the open issue, which maybe is the most interesting for the future, is how far can we go with this lifting approach? Are there other problems that we can basically address with this kind of idea? Okay, thank you.
Well, thank you. I'd like to apologize. I had to take care of a room problem because of our delay, but it's been taken care of. Other questions? Yes.
No, so we didn't. We for our solutions, we made experimental tests. I mean, we had experimental data and we validated the approach, but we didn't make comparison of the two methods. The idea is really that in this case we are able to guarantee global convergence since we are in the linear framework. We know also that there were other solutions. For example, the second solution that we also developed with Rob and other colleagues, in which we could not ensure global convergence, but we didn't make the comparisons of the approach for the data.
Yes.
So you talk about the homography up to a scale.
Yeah.
Question
the scale, we can compute the scale, in fact. Yes, we can, the normalization, basically there's a result in computer vision that tells us how to scale the homography. So that's something that can be computed. Sorry? What I mean is that basically h, or the scale, h times, so the scale which allows to project in the special linear group, this scale factor can be computed from h.
Thank you very much.